and some other topics of interest. Today, he will talk about anonymous scaling regime for one-dimensional Mott variable range hopping. And before I hand the platform over to David, I would like to remind you that we have this the PDF file of the slides is available at the Probability Victoria Seminar website. And please mute your microphone. Thank you. I hand over to David. Please, David. Thank you.
Okay. So, well, thanks for the invitation and the introduction. So, yeah, I'll be talking about Mott variable range random hopping. And so this is a particular model of random walk in random environment, which I'll introduce in a moment or so. And so, yeah, part of the talk is to describe the results for this particular model, but also part of the talk is to, part of the motivation for the talk is also to introduce a kind of more general method for proving scaling limits of simple random walks on sort of various graphs and so on. And so, in particular, this is going to be based on the sort of well-known connection between random walks and electrical networks. And so, yeah, the second half of the talk will be focused on this part of the story. Yeah, and before I start, I should say, just highlight that all the kind of new results for the model are joint with Ryoki Fukushima and Stefan. So they were both in Kyoto up until recently and now have moved to University of Tsukuba. And yeah, maybe special thanks to Stefan, who's I see in the audience here today. So many of the pictures in the slides and all the simulations were due to him. So yeah, thanks for that. So yeah, so let's start with the model. So here's the basic model. So it's kind of quite a simple setup. So it's essentially, well, the underlying state space is going to be just the points of a Poisson process. So our random environment is going to be made of the atoms of a one-dimensional Poisson process here. So these are just shown here along the line. And we'll, just for convenience, assume this is sampled according to its palm measure. So we'll have a particle at 0 here. And so in particular, all of the gaps here between these kind of sites, sorry, I should say rather than particles, these are kind of exponential row random variables, of course. And so that's the environment, and the process that we study on this is a continuous time random walk. So this is jumping at rate 1, so holding times of 1 everywhere. And we're going to jump from site to site, so we can jump from any site to any other site. And the probability of jumping is given by this expression here, and the conductances, so you see omega I, omega j's, are just given by the exponential of minus the distance between these. Okay, so you're kind of, the chance of jumping from site to site decays exponentially with their separation. Okay, and it's kind of easy to check that for the Poisson process, then the kind of normalizing constant that you need to make this a probability is finite almost surely, and so this is kind of a well-defined probability measure at each site, and we can sort of define the random walk in random environment using these probabilities. Okay, so this is the basic model, and like with kind of many models of random walk or random walk in random environment, the kind of natural question is to sort of ask about what the asymptotic behavior, what the kind of scaling behavior of this process is, and that's going to be what I hope to describe for this particular model. So yeah, just a bit of background before I do that. So why is it called the Mott random walk? Well, it's because it was introduced by Mott, in some sense anyway. So he was a physicist, and he was using it, or he was using it to describe electron transport in non-crystalline material, and in particular kind of explain sort of the phenomenon of semiconduction and so on. And in particular, his kind of model was that somehow that he was considering kind of the system in some kind of localization regime, so that the omega I and omega j's here, these are kind of sites at which the electrons might localize, and he's kind of interested in the hopping behavior of electrons within the medium. And so his kind of basic model was this should depend on the separation spatially, so that's the term that I wrote down on the previous slide, and also maybe the energy separation. So we have some function of the energy difference between the two sites here, and the kind of effect of this might depend on the temperature. Well, beta is the inverse temperature. Here, and of course, being kind of an electrical system, you could also introduce an external field here. So a positive lambda, for example, would give a kind of drift to the right of the particles in the system. And so, yeah, the basic question is to kind of explain the kind of diffusivity of the model. So how the particles diffuse through the medium as we sort of change the model parameters. And I guess his main focus was actually on the temperature parameter to here, but of course it's natural to ask about the effect of all the parameters in the model. And I should also say that, I mean, I'm talking about the one-dimensional model. Of course, it's very easy to generalize to other point processes omega here, and in particular put these in higher dimensions too. So you can easily just put down the Poisson process on RD and ask the same kind of questions. And yeah, just kind of to underline, so exactly he was interested in sort of this kind of non-crystalline material. So just for sort of basic comparison, of course, we know that if we have a kind of a more regular structure and we ran the same kind of process, then let's suppose we just kind of normalize the lattice to have the same density of particles. It's still nonetheless the case that somehow, at least in the simple case where beta and lambda are 0, then this is just going to be kind of a simple random walk, and the increments are just going to be given by some distribution with finite variance. So we have a functional central limit theorem for the particle here, and so in particular convergence to Brownian motion. And yeah, so it kind of becomes of interest to compare with the effect of introducing this inhomogeneity into the medium, as we do by kind of perturbing the kind of lattice here to the sort of one that we get by looking at the Poisson process. Okay, so that's the sort of yeah, basic model and thought behind it. And yeah, it turns out that this introduction of the inhomogeneity does have a significant effect. So like I say, in the sort of regular lattice case, it doesn't matter what the density is. Of course, we're going to still have a random walk with finite variance. It's still going to converge to Brownian motion. But it turns out that for the sort of the Mott model, this isn't true. And so actually, the behavior of the process depends quite sensitively on the density. So this is a parameter I'm going to be focusing on in this talk. And so in particular, when rho is bigger than 1 here, for almost every realization of the Poisson process, it turns out that if we look at the Mott random walk, and we rescale it in the usual kind of diffusive way, so kind of n squared in time and 1 over n in space there, then this converges sort of as would the simple random walk on the lattice to a Brownian motion. And in a sense, the only effect of the randomness is the diffusion constant here, this sigma, which of course depends on rho, but it's deterministic. And so exactly, we have kind of homogenization somehow, that the randomness of the environment evens out somehow in the long time behavior in this regime. On the other hand, if we kind of lower the density, so we take rho below 1, actually in this same paper by Caputo Fagginato, it's shown rigorously that the same result is true in a slightly weaker sense, so kind of almost sure, I mean, in probability with respect to the environment rather than almost surely. Then the same is true, but the diffusion constant is 0 here. And so in particular, on the diffusive scaling, the limit is trivial. And so the process is sub-diffusive here. So actually, I should say in this paper as well, they study also the effect of the sort of beta parameter I wrote down before, the inverse temperature, and also kind of explore, they provide an expression for this variance and explore the asymptotics of this with the beta parameter as well. And so, yeah, there's kind of interest in that direction too, and that kind of relates to what Mott was originally doing. But the interest for us is actually going to be exploring in this sub-diffusive regime, what's the kind of right scaling that we should be making to see a non-trivial limit. And basically, our main result is summarized here. And so I write for rho less than 1. Actually, we can also deal with the boundary case as well. I just don't for sort of convenience to keep the statement clean here. But in particular, it turns out that if we rescale, the right time scaling to take is now in the time rather than n squared, we're going to take n to the 1 plus 1 over rho. So of course, this is bigger than a square. And so we're kind of, to get a distance n away, we're needing to run a bit longer. But if we rescale on this time scaling, then we can also describe a functional scaling limit for the Mott random walk. And so the aim of this talk will be to describe what this this process is, and also we'll see kind of in the method of the proof, it will kind of explain how the inhomogeneity of the environment kind of persists in the limit to give the particular process that I'm going to write down. And I should say that the convergence here is slightly weaker than what holds in the homogenization regime, and that we can only prove this, and it's only actually true under the so-called annealed law, where we average out over both of the process here and the environment. Okay, so that's the kind of result that I'm going to build towards. Yeah, so actually just one small comment as well about the model. So I mentioned briefly, like we could also consider it in higher dimensions. Actually, it turns out that of course, again, you can ask the same question in higher dimensions. It turns out that in higher dimensions, you always have homogenization. And so you never see this sub-diffusive regime. And so what I talk about today is really just a sort of phenomenon of the one-dimensional model here. Okay. So that's the kind of a brief overview of what's going to happen. And before I get to the actual kind of method that we're going to use, I'm going to actually spend a part of the talk on actually describing what happens in a simpler model, because I think this is quite informative about what happens and why the limit that we see is actually the limit that we do see. And so for the minute, I'm going to consider the simplified model. So in particular, I'm going to keep the same, sorry, that was meant to be one line, let's try that again. So I'm going to keep the same Poisson process here, 0, omega 1, and so on. But I'm going to now just consider the conductances between kind of nearest neighbor sites. So I'm just going to consider the very much kind of simplified graph. So now I just have conductances along the sort of edges of neighbors here, and I'm kind of throwing away all of the possible kind of edges or other possible jumps in the model. Okay, so this of course hugely kind of simplifies the graph and means that we're kind of really looking at a one-dimensional graph rather than kind of the complete graph on the point process. And so at least the kind of a basic kind of intuition, this is going to be a kind of a useful thing to do. And well, it kind of allows us to start thinking about what kind of properties of one-dimensional processes are important to understand their behavior. And so just as a reminder, so maybe this is familiar to some or many of you, in the setting of one-dimensional diffusions, there's just a few kind of basic properties that essentially characterize their behavior. And so in particular, if we don't allow any killing for our process, then the two basic quantities or objects that describe their behavior are given by the scale function and the speed measure. And so the scale function is, of course, kind of capturing its harmonic properties. So just on the kind of maybe kind of simplest way to kind of characterize this is exactly just in terms of its hitting properties here. So if we start from a site X and we ask what's the probability of hitting Z before we hit Y for 3 points like this, then the scale function appears in this way here. So we just kind of measure the distances in some sense from X to Y there and from Z to Y there. We look at that ratio, but not in terms of the Euclidean distances, in terms of the sort of distance, in terms of the scale function here. And so, of course, in Brownian motion, the scale function's just the identity, and we can put any diffusion on its natural scale by just kind of applying the scale function to it. Okay, so that's the role of the scale function. On the other hand, we have the speed measure, which is, in a sense, telling us where the process is liking to spend time. So in particular, where the speed measure is great, then this is where the process likes to live. And so, well, because Sz is now a diffusion on its natural scale, it turns out that this means it's a Brownian motion time changed by some measure. And actually, it turns out that the measure that we should be looking at is, of course, just this invariant measure pushed forward by the scale function here. And so again, this is kind of maybe not that informative if you've not met time changes of Brownian motion before, but roughly speaking, well, we can construct this in the following way. So we look at the additive functional given by integrating the local times of the Brownian motion against this particular speed measure on the right scale here. We take the inverse of this and apply this at the Brownian motion, and this Brownian motion, this will be a process with the same kind of sample path as Brownian motion, but with sort of speeded up and slowed down, so that the invariant measure is given by this M inverse, M composed with S inverse here, sorry. And of course, this also gives a construction of the Z process, because we can just move the S over here and give S inverse composed with this Brownian motion, gives us a construction of the one-dimensional diffusion with these characteristics. Okay, so this was the picture of one-dimensional diffusions. And why have I spent 3 minutes on this? Is because we can actually start to think about these things for the kind of at least the nearest neighbor of the Mott random walk quite easily. So in particular, if we start to think what the sort of scale function of the Mott nearest neighbor version of the random walk is, this is kind of a very simple computation. So again, if we're thinking of asking what's the probability started at omega j that we exit at omega k, or sorry, we hit omega k before we hit omega j. So this is meant to be started from omega I in the process. And then it's a sort of simple calculation. So there's many ways to do this. I mean, just a simple induction will answer this question, but this is kind of essentially a gambler's ruin type exercise, of course. And we can compute it again just by looking at the ratio of the sort of distances here in the graph between these two lengths here. But the right kind of distance we should use, of course, is the effective resistance on the graph. And so that's what's given here. So of course, the conductance is 1 over these is the effective resistance of each edge. And so to get the effective resistance of the whole segment here, we just sum them up over the segment. And so it's kind of a basic problem in random walks to kind of compute this kind of exit probability. And so in particular, this is kind of telling us that the scale function for the process is actually the kind of given by the effective resistance here. So, I mean, just to make it, to give us the right increments, we're going to kind of give this a sign. So in particular, we're kind of just going to, if we kind of have the points here, omega 0, omega 1, omega 2 or something, we're going to call the scale function just the distance, the resistance distance from the origin here. And on the negative side, we kind of want to make this negative just to give us an increasing function, so that in particular, the sort of increment between omega I and omega j here always gives the effective resistance between them. Okay, so that's the sort of natural scale function. And of course, this is just, in the nearest neighbor case, this is just an IID sum of random variables. Each of these conductances are kind of each of them minus the distance between these things, and these are just exponential random variables. And so we can compute the tails of these. So they were exponential random variables with intensity rho, and this turns out that these nearest neighbor resistances are just heavy-tailed random variables, at least in the sort of rho less than 1 case here, with this kind of polynomial tail. Yeah, okay, so that's the u bigger than 1, of course. Here, and so of course, what this means is that if we look at the sort of scaling limit of this scale function, then this is going to, on the scale of n to the sort of -1 over rho here, look like a stable subordinator. So it's going to converge to a rho stable subordinator. So in this picture here, sort of the rough picture is I've got kind of distance about n along the top there. I've got kind of rho n particles. In the deformed space, the kind of number of particles, or sorry, the resistance distance, sorry, across this interval should be kind of n to the 1 over rho. And of course, in this kind of heavy tail regime, we know that these kind of the largest kind of intervals that we see, so these intervals, if that was omega I plus 1 minus omega I, this is kind of being exponentiated in the resistance here. And the kind of largest ones of these are of course the same order as the sort of total sum of the resistances here. So these kind of large intervals kind of really give a non-trivial proportion of the kind of overall resistance between points. Okay, so that's the kind of basic picture for the scale function. And just as a kind of comment, just like in the continuous case, when we kind of look at the process on the kind of, in terms of this resistance scaling, kind of if we kind of plot the coordinates as I've done on this kind of deformed space here, then just by kind of construction, this is the martingale down here. So we would expect it to converge kind of under appropriate scaling to some time change of a Brownian motion. So that's the kind of basic idea. As for the invariant measure, this is kind of more simple. So the particles have the invariant measure given by the sort of sum of conductances out of them. This is bounded in this case, and so we just converge to Lebesgue measure. So this is kind of very simple. Multiplied by some constant. So that's not yeah, particularly interesting. But what it means is kind of what we would naturally then guess in terms of what properties might the limiting process have. And we might guess that these kind of properties transfer to the limit. So it would be natural to expect that the limiting process should have the scale function given by this subordinator and the speed measure given by Lebesgue measure here. And so in other words, we can construct it exactly as I wrote down before from these two objects here and the Brownian motion. Again, of course, you can kind of worry because a subordinator is, of course, not a continuous process, but actually such kind of generalized diffusion processes, we have kind of Cadillac scale functions, and indeed atomic speed measures were kind of constructed quite a while ago now. So Ogata in the 80s has a paper where he constructs such processes, and so this kind of falls into kind of a class of generalized one-dimensional diffusion processes. And a little bit more than that, actually, the generator of these kind of one-dimensional diffusion processes in general, of course, is given by d by ds, d by dm. And so this kind of means that somehow the time scaling of the processes should be something like the mass scaling times the scale function scaling. And so somehow that feeds in down here. So the n times the n to the 1 over rho here is just really the mass times the resistance scaling for the discrete process. And kind of the kind of heuristic suggests this is the scale that we should be looking at. Okay, so that's the basic kind of heuristic idea as to why this is the process that appears and where it comes from. Yeah, so this is actually a non-rigorous kind of argument at the moment. I actually think that in the nearest neighbor case, we could make this argument rigorous, but I mean, there are kind of various kind of Markov chain approximations to one-dimensional diffusions and so on that we could have thought of building on to prove this in kind of a truly one-dimensional kind of way. But the reason we didn't, of course, is because actually the true process we were interested in is not this nearest neighbor model, but the Mott model. And so there, the graph really isn't truly one-dimensional. Like I said, it's the complete graph on the Poisson process. And so yeah, we needed to take a slightly more sophisticated view of the problem to kind of achieve the sort of corresponding result there. Okay, so that's going to be what I describe in the second half of the talk. Yeah, just one more kind of. Oh, so here's actually the simulation. Sorry, I forgot I had the slide, but yeah, this kind of gives you a bit of a flavor of what the process is looking like. So the two pictures here, we've got the sort of the Poisson process along the bottom here. So this is kind of space along the bottom and time on the side here. And the sort of gray vertical lines are kind of corresponding to the localization site. So the kind of points of the Poisson process here. And you can see that we plot them in Euclidean space on the left and according to their kind of resistance distance on the right there. And so in particular, you can see some gaps that are sort of slightly larger. So there's a slightly larger gap here that's going to map over when we kind of exponentiate it again over to some kind of bigger gap in the picture on the right there. And you can kind of see that on the right here, we have a Brownian motion, time changed, to sort of live on these lines here, basically. And so you can see that, of course, let's look at sort of maybe this kind of section of time here. You can see that the Brownian motion will be making excursions into this gap here, but these are kind of instantaneous. So these are kind of not seen in the sample path here. And so, of course, when we kind of look back over in real space, these kind of gaps disappear in the limit, and it just looks like we're reflecting here off a line. And so actually, yeah, maybe that's not the best one to choose. Maybe someone like this one down here is a slightly better one to choose, in the sense we're kind of going to bounce off one side of the line for a while, but then at some point the Brownian motion makes an excursion over to the other side here. And then we kind of move from one side of the barrier to the other. And so where we were reflecting on the sort of left-hand side here, then we kind of reflect. So on the left-hand side there, we then reflect on the right-hand side afterwards for a while. And so this is the kind of basic, well, the basic property of these processes, and how we see this kind of, like I say, the persistence of these kind of edges of large conductance in the, or smaller conductance, I should say, in the limit. Okay, so that's the basic picture. Yeah, and one other kind of just small comment before I go on to my main argument is, yeah, this kind of idea of deforming the space into kind of a more natural set of coordinates kind of connects to other areas of study of random walk in random environments. So yeah, so this slide was taken exactly from Stefan, which is why it looks a little bit different to my other slides, but I was a bit lazy to write it all again. But yeah, in particular in the study of, for example, simple random walk on a supercritical percolation cluster, the basic strategy, so just for those that aren't familiar, I guess most people are, so percolation is just, we'll look at the integer lattice, we'll include edges with probability p, take them away with probability 1 minus p, and we'll assume that we're in the regime of supercritical percolation, so we have an infinite cluster, and we study the random walk on this. And so the sort of basic strategy for kind of proving the diffusiveness of this is to kind of write the random walk in terms of a martingale part and a corrector part. And so the martingale kind of is then, again, it's kind of the standard machinery for showing martingales converge to Brownian motion that can be applied. And the sort of often the more challenging part of the question actually is to show that this corrector term, so the part that's left over, vanishes. And so that's the kind of basic strategy. And in some sense, this is a bit like our viewpoint of the Mott random walk, in the sense that we kind of introduce a random deformation of the space. So we can kind of view this psi here as a deformation into harmonic coordinates. So in the nearest neighbor model, the resistance metric exactly corresponds to the harmonic coordinates for the process. So namely, under which we have a martingale when we apply it to the process. And then what we want to do is somehow find a way. So in the percolation, the goal is to show that the corrector vanishes. In our problem, it's of course not quite so simple. We actually have what the issue is actually finding a way to map back from these harmonic coordinates to the original coordinates. And so that's exactly what's given by this kind of inverse of the subordinator map here. And so that's maybe the difference, but also the kind of connection to these kind of other approaches in these problems of random walking in random environments. Yeah, so that's the kind of heuristics. But yeah, now in the second part of the talk, what I want to do is get on to talking about how we actually deal with the Mott random walk itself. So yeah, let's just recall. So what the model is, we've got our Poisson process, and between omega I and omega j, we've got these conductances of the form e to the minus omega I minus omega j. So that's a bit unclear. And so we have a complete graph on these Poisson processes. And so now, to characterize the effective resistance, we can't kind of just compute it simply by the series law. We have to use the, like I say, slightly more sophisticated viewpoint of the problem. And in particular, we're going to define this in terms of the sort of usual variational kind of expression for the effective resistance. So in particular, the Dirichlet energy. So if we hold the sites here at voltages according to F, then the energy dissipated is given by this Dirichlet energy. And well, the effective conductance is given by holding the two vertices of interest at voltage difference 1 and asking what's the sort of minimum energy dissipated. And well, 1 over that is the effective resistance. So this is just the usual kind of, or a usual variational characterization of effective resistance. And what kind of is going to be the main ingredient to our proof of the main result is actually to show that this effective resistance in this kind of, in the more general Mott, in the true Mott setting, actually has essentially the same scaling behavior as the nearest neighbor model. So in particular, if we look at the increments of the process and we rescale them appropriately, then these exactly scale to the increments of a stable subordinator. And yeah, if you're worried about the topology in which we prove this result, this isn't quite the precise statement, but this kind of gives the right idea as to what we're actually going to prove. And yeah, the basic idea is somehow to basically try and reduce the problem, of course, to something that looks a bit more one-dimensional. So, of course, there's several kind of problems that you have to deal with. So in particular, like I say, the graph is not a one-dimensional graph, so we don't quite know, for example, what the actual effective resistance is between neighboring vertices. So in particular, the kind of effective resistance between two neighboring vertices, say here and here, is contributed to by all of the edges actually in the graph. And so we can't kind of quite reduce it to a sort of simple expression based on individual edge resistances. And so actually, one part of the story is to show a good approximation. So namely that this looks something like the nearest neighbor resistance multiplied by some, so this is meant to be a psi I here. And so we multiply this by some correction term that we can sort of understand or control well. But like the other thing that we want to do, of course, is to show that somehow if we look between 0 and n, we want to show that this is approximately something like the sum of these random variables. And of course, again, we don't have independence of these random variables. Well, anyway, the resistance doesn't sum quite so simply as this in this kind of more complicated model. We don't just have the series connections. And so, yeah, I don't know that I want to spend too long on this, but the basic strategy is, I mean, because we know that somehow the big resistance is going to come from these kind of exceptional edges in some sense, the jumps of the subordinator in the limit, then we kind of start off by just kind of restricting to these. We look at these, and we can also show that these are kind of far enough apart that we can kind of throw away many of the edges around these to somehow decouple the resistance between the kind of individual terms that are important. And so we kind of reduce somehow the problem to something that is a bit more one-dimensional. So yeah, I kind of reduced this to one page of the slide. In the paper, this was kind of quite a challenging exercise, and actually is one like where I guess the main challenge for establishing the result that we do comes from. But somehow intuitively, the idea is fairly simple, as I just described. And yeah, maybe a slightly better way to understand this now is because, like I say, we're not really looking at one-dimensional objects anymore. Is to not look at this as a subset of R, but to just look at this as a metric space equipped with a metric given by the resistance here. And so rather than looking at it, like I say, as points embedded into R up here, we look at the points in terms of their resistance metric. And what I just kind of described is that at least asymptotically, this looks exactly like the picture I had before. So somehow it looks more or less like a one-dimensional picture here, where the kind of atoms of the environment here map down to the sort of image of a stable subordinator here. So somehow this metric space asymptotically looks exactly like I say, this kind of range of a subordinator here with these kind of gaps in the space corresponding to these kind of edges of large resistance here. And so yeah, so this is actually something we can prove rigorously, and like just for the technical background, we prove this in sort of usual kind of Gromov-Hausdorff type topology, which of course doesn't rely on being able to isometrically embed one space into the other space, of course. And so that's why we look at it in the slightly more abstract metric space viewpoint here. Okay, so that's the kind of main ingredient. And once we have this, actually, this is kind of turns out to be more or less enough to get the scaling of the random walks. And so here's the kind of machinery now that is going to allow us to do that. And so, like I say, this is kind of a general approach that kind of has been developed over recent years. So it goes back to the study of random walks on fractals and understanding the construction of diffusions on things like the Sierpinski gasket from the random walks, and has since been kind of adapted to sort of apply more generally to sort of random state spaces. So somehow the methods have kind of improved to the point where we can tackle some the problems are kind of quite robust for like I say, the sort of local details of the problem. And so here's the sort of basic setup. So like I say, in the context of analysis on fractals, it was introduced by Kagami in, well, I guess the 90s or so, the idea of a resistance metric. And so this is kind of a natural generalization of the resistance metric on a graph to a general set. And exactly, he was studying, the limits of stochastic processes on graphs. And so this kind of was a natural object or natural kind of concept to introduce. And so the definition is kind of fairly simple. So we take any set and we say that a function on, well, f cross f to the real line here is a resistance metric if for each kind of finite set, so if I take some finite collection of points V here within the set, I can define conductances between these such that the function when restricted to these vertices is just the effective resistance for that graph. So it's just saying that a resistance metric on a set is just kind of a natural extension of resistance metrics on the sort of graphs within that, or can be kind of seen as an extension of graphs resistance metrics within that set somehow. And so, yeah, kind of simple examples of this. Of course, the effective resistance metric on a graph is itself a resistance metric. So this is not quite an empty statement in the sense we have to kind of worry about the consistency of resistance metric under kind of some subsetting operations, but this is kind of a fairly straightforward thing to check from the variational construction of the resistance metric. Another kind of very simple example is the one-dimensional Euclidean case. So again, what we want to check is that if we have points, say x1 up to xn here, we can put conductances between these so that the kind of associated resistance metric is the effective resistance, the Euclidean distance. Sorry, and of course, to do that, all we're going to do is to between the nearest neighbors, say that the conductance is 1 over their distance here. So in other words, the resistance is just the distance between them, and then we just use the series law to see that the Euclidean metric is just a resistance metric according to the definition I wrote down before. And yeah, just to kind of highlight, this is kind of a low-dimensional concept in some sense, is that this is not true in higher dimensions. So we can't define the Euclidean distance in terms of a resistance metric in higher dimensions. And somehow the key, when I say low-dimensional, is actually it means that the processes we can construct using these are all going to be point recurrent. And so this is the sense in which, or the kind of spaces, that we can deal with using this kind of framework. Yeah, so although I'm not going to talk about them here, just to kind of illustrate, we can do some more interesting things. We can also talk about trees. So any kind of natural tree metric will be a resistance metric. And like I say, this was developed in the context of fractals, so we can construct a resistance metric on things like the Sierpinski gasket, Sierpinski carpet, and so on. Okay, so this is the sort of basic object that we're going to look to define the limit from. So we'll just move down. And yeah, why this kind of connects to stochastic processes is because exactly as in the kind of graph case, we can connect to from the resistance metric to a so-called resistance form. And so this slide is slightly abstract, but a resistance form is just going to be a quadratic form on our space. So F is going to be its domain, and we can kind of connect it with the resistance metric exactly as we did on the graph case here. And so, yeah, I'm not going to write down the definition of this because I don't think it's very helpful for like just, yeah, in a very kind of short time to see the list of properties you need to be a resistance form. But somehow from the point of view of stochastic processes, the kind of key point is that actually these are nice in the sense that, let's just look at the compact case for a second, then it turns out that these resistance forms are basically Dirichlet forms. So in particular, if we restrict to, so if we have a Borel measure, say, of full support, then it turns out that these resistance forms are exactly Dirichlet forms on the relevant L2 space. And so, of course, from that, we know that we have a kind of natural connection to stochastic processes, of course. And yeah, there's a slightly more complicated version of this statement as well for locally compact spaces as well. And so just as kind of very simple examples, again, I won't spend too long on these just because of the time, but the first kind of natural example, the simplest one, is just to sort of look at the Euclidean metric, so the one-dimensional one. In this case, it's just an easy exercise to check that this variational characterization of the Euclidean metric, so it corresponds to the sort of standard Dirichlet form. Of course, this is just an undergraduate calculus exercise to check that if we compute the right-hand side here, then then we get back the Euclidean metric. And similarly, in terms of connecting to stochastic processes, of course, we know that this Dirichlet form is basically the one that corresponds to Brownian motion. So in particular, if we integrate by parts, then actually for any measure m, we can write it down in this way for appropriate functions, I guess, inside here. But and in particular, the delta here is just the sort of second derivative here according to, well, d by dx and d by whatever the measure we're putting there. So in particular, if this was just the Lebesgue measure, then this would just be the usual second derivative and we'd have Brownian motion. And, well, with the boundary conditions up and down, in this compact case, we get Brownian motion on 0, 1, but if we look at the kind of the locally compact case, we can also construct kind of Brownian motion on the whole line in this way. The second example is, of course, if we have the resistance metric on a graph, then we just get the continuous time Markov chain that we want. So we have the conductances corresponding to the effective resistance metric here, which are determining the probabilities. And if you also have the measure, then this, of course, is determining the time scaling of the Markov process down here. So in particular, when this m is just this sum of conductances, this is just the process that's jumping at rate 1 from each side. Okay, so these are going to be the two examples that we use, and here's just kind of a brief summary of what I said. So basically, given a resistance metric and a measure, then this gives a resistance form, which is a Dirichlet form, and that gives us a strong Markov process, and we can get that from the generator down there. Okay, so we have this strong connection between the resistance metric and measure and the stochastic processes. And it turned out that it's kind of strong enough that if we know that the resistance metrics converge, so let's suppose I've got a sequence of spaces. So here we've got Fn Rn is just a metric space, a resistance metric space, sorry. Mu n is just going to be a measure on this space of full support. Rho is going to be just a marked point from where I'm going to start my diffusion. And well, because we don't, these spaces that I'm going to look at are not necessarily kind of embedded within a bigger space a priori, I'm also going to include a map here, phi, that sort of takes Fn and embeds it, so FNR in here, and embeds it into Euclidean space. And so in this case, equipped with the Euclidean metric continuously. And so this is just going to give me a kind of common space to study the processes. And like I say, the sort of connection between the resistance metric and the processes is strong enough that it turns out that if we have convergence in some suitable way, so again, some kind of Gromov-Hausdorff type notion of convergence of these sort of abstract metric spaces, then we also get convergence of the processes. So here, the xn here is just the sort of process naturally associated with this resistance metric space. We start it from the marked point, and then we map it into R using the embedding here, phi n. Yeah. What the result says is these are going to converge to the corresponding thing for the limit over here. And so, yeah, I've written it down here. So this is actually a theorem for compact spaces. Again, we can kind of generalize to locally compact spaces. You have to worry a little bit about explosion and so on, but we can handle that. Yeah, just in case you're interested, the map R here, like the fact we're mapping to Euclidean space, one-dimensional Euclidean space is not particularly important. We can map to any complete separable metric space we like for this result to be true. Okay, and well, if you cared about the metric, here's the metric. I have it in the slides, but maybe again for the time I have left, it's not so interesting to explain. It's a natural notion of convergence, the sort of metric spaces. So yeah, in the last 5 minutes, hopefully I get time to explain how we apply this result to the Mott random walk. And so here's the kind of objects we consider. So you remember we had the set, the measure, so the resistance metric, the measure, the marked point, and the map. These were the kind of objects we had to consider. And so, of course, in the current setting, the set we want to look at is the points of the point process, the Poisson point process. The Rn is going to be my kind of rescaled resistance metric on these points. The μn is going to be my rescaled invariant measure for the random walk here. And so I should say all of these kind of scalings that I'm given are kind of for looking over an interval of n points, I should say, in the Poisson picture here. So as we kind of computed before, the kind of resistance distance is on the order of n to the 1 over rho. The kind of scaling of the measure is linear in the number of points. We kind of fix a marked point, so rho or omega 0 is just our kind of starting point. And we then want to embed our spaces into Euclidean space, one-dimensional Euclidean space, but of course they're already there. And so we just take the identity and, well, but to fit with this kind of scaling of n points here, we want to kind of scale things by 1 over n, of course, because that's means the point of kind of distance n away is going to be distance 1 away, of course, asymptotically. And like I say, although this kind of seems kind of a bit superfluous to include this kind of identity map here, and of course the real reason we do it is we're not really viewing it as the identity map, we're viewing it actually as a map from this resistance space at the bottom here, which of course isn't really one-dimensional in the kind of, well, before we get to infinity, as it were, n is infinity. We're really viewing this identity map as a map from that deformed space up to the kind of original Euclidean embedding of the points. And so that's the point of including this map here. And well, when we kind of think about it for a second, the associated process that we were able to kind of read off from this object is actually just the Mott random walk with the scaling factors in the places we want them. So the n to the 1 plus 1 over rho is coming from the resistance and the mass scaling. The 1 over n out the front here is coming from the kind of spatial scaling over here. And yeah, this is how the scaling factors feed into the associated stochastic process. So yeah, like I say, we've shown that the resistance metric converges to space converges to the picture here. So namely just the image of a subordinator equipped with its kind of usual Euclidean distance down here. We know that the kind of invariant measure was converging to Lebesgue up on the top line, and so it converges to the kind of image of this down here. So S rho is mapping these points up here down to the deformed space. And so that's the sort of measure on the bottom line here. And to get back, of course, from this deformed space up to the original space, we want to map back up by S rho inverse. Okay, so that's the map that we need to apply to go back, and that's the sort of object that comes in the limit. And again, if you kind of plug it through all the definitions, the fact that we've got Euclidean distance here means we've got our Brownian motion. The fact that we've got this measure constant times S rho inverse here means we should time change it by that measure. The fact that we've got this map here means that we want to apply that out the front here. And this is, of course, just the same form as the kind of one-dimensional diffusion with this scale function S rho and the Lebesgue measure, the speed measure, or constant times the Lebesgue measure as its speed measure. Yeah, and so that's why we get that as the limit. And yeah, so maybe just to kind of conclude with the main result. So that's what we end up seeing, and indeed, kind of these are the kind of sample paths again that we saw before in the nearest neighbor model. We have the same limit appearing here. Yeah, maybe just to finish, sorry, just with a couple of concluding remarks. So I talked only about the case rho is less than 1. Actually, the same arguments will give us the limit for rho bigger than or equal to 1. So when rho is bigger than 1, the resistance then, I mean, the kind of nearest neighbor resistances now have a mean, and so we could just get kind of law of large numbers, so we get kind of linear scaling for the resistance. And so we just see, we replace this subordinator here with just the identity map, basically, everywhere, and everything's just ground in motion. In this case, we can also generalize the point processes. We can also include energy marks and include a vanishing version of the drift, which actually gives the drift in the limiting process. We can check that quench convergence doesn't hold, and well, we also believe there's kind of aging for the model, but maybe I'm a little bit over time, so that's where I will stop for today. So yeah, thank you
very much
coming on.
Thank you. Okay, question time. We can ask questions. If you have any questions, please ask.
So the conjecture on aging is, I mean, the picture you have is something which sort of hangs around at a boundary because it can't get across it in a way.
Yeah.
And so it's not quite the same as having a trap where it's sort of held in on both sides.
Yeah, so exactly. So yeah, so thank you for giving me the chance to explain what this is. So exactly. So the kind of usual kind of conjecture on aging that you see for models like the Boucher trap model, exactly where you're kind of trapped at a site for a long time before you move, would be exactly the same statement, that if we look at the relevant time scaling, if we look at where we are at some time and some slight time later, say time 1 and time some constant multiple of this time later, then we're likely to be at the same site, because the trap that we're in has the same kind of order. The time that we're in the trap has the same kind of order of the time that we spent up until that point. But yeah, so actually, yeah, so this kind of bar on the top here is actually, of course, just meaning that I mean the running supremum of the process. Yeah, and so what's going to kind of happen for the process is up until, let's say, time 1 on the right scaling, of course, the process is going to find some barrier, and so it's going to kind of reflect off this barrier for that time. And so what the conjecture is actually that the running supremum at some kind of multiple of this time later, so this is kind of time 1. Yeah, when we look at kind of, well, I guess h minus 1 later, then the conjecture is that actually there's kind of a non-zero probability of having, not crossed this interval by that point. And so exactly the kind of, whereas in the kind of more sort of standard statements in some sense of aging, the kind of localization is happening at sites, this is kind of saying that the aging is in terms of the kind of the extremum that we're reaching. Kind of.
Right, so you force the sort of left-hand thing by making the running supremum. And then
yeah, exactly.
Okay.
Exactly, and of course, yeah, we expect this kind of probability of this to go to 1 and 0. Of course, as h goes to 1, I guess, and infinity. Yeah, so that's the statement.
Okay, any other questions, comments?
I have a comment.
Yeah.
Which is that I'm old enough to have actually known Neville Mott. He was in the same college at Cambridge. He was a distinguished ex-master, and I was a young research fellow. So.
Okay.
Okay, that's nice.
Okay.
All this kind of information, we don't really know. Just must be direct from you guys.
Interesting.
Okay, if we don't have any questions or comments, let's thank David for the talk again. Thank you. Thank you.
Okay.
All right. Thank you very much. And Kostya, I hand over to you. Do you have any announcement?
Not yet. Thank you. Thank you, everybody. Not yet, but
okay.
something will come up soon.
Okay. All right. Take care. Okay.
Your help.
Thanks,
bye. Okay. Bye-bye.
Bye-bye.
Bye.
Okay,
Thank you.